All right, we're going to go ahead and take a look at the homework for 4.5. So these are optimization problems. First problem, it says consider the following problem. Find two numbers whose sum is 23 and whose product is a maximum. So they want us in this first part to just complete filling out this table. So if our first number is 1, then our second number has to be 22 because they have to add up to be 23. We multiply those two together, we get a product of 22. If we let our first number be 2, then our second number needs to be 21 so that they add up to be the 23 again. And we multiply those, we get 42. I can keep on doing this, trying to figure out what's going to happen. So if I let the first number be 3, then the second number has to be 20. And multiply those together, we get 60. So it looks like these are the products are getting bigger and bigger as we go. Let me try 4. If this is 4, then this has to be 19. If we multiply those together, I may as well get my calculator out here because I'll probably need it. All right. Oh, man. All right, so we get 76. So again, it appears that they're getting larger. If our first number is 5, then our second number has to be 18. And we do 5 times 18, and we get that 90. So again, they look like they're getting bigger and bigger. 6, this has to be 17. We get 102, 7, and 16 is 112. So maybe there is no combination that these just keep getting bigger and bigger and it doesn't matter, but we'll see here what's going to happen. 8 and 15, multiply those together, we get 120. And then 9 and 14, we get 126. 10 and 13, 130. 11 and 12, we get 132. So it looks like the maximum that we would get is if we do this one right here. If we let one numbers be 11, the other one be 12, we get 132. Because if we keep on going with this table, the next number would be 12, but then the other number would be 11. We've already done that. So it looks like that's our best answer. Smallest number 11, largest one is 12. However, this is not correct. There are some other numbers that will get us even bigger number, but they're not easy numbers for us to just look at visually and identify. So we're going to use calculus now. So here's what we need. We have two numbers, x and y. We need them to add up to be 23. So this is our, what we call a constraint equation. Okay, we have to have those two numbers add up to be 23. But on the other hand, we want to try and find the maximum product, so the largest number we can get when we multiply them. So P is the thing I'm trying to find the maximum of, the maximum product. And so we're trying to optimize this function. To do this, what we're going to have to do is look at this equation, and we're going to have to rewrite it so that we only have one variable. Right now we have two variables, x and y. So what I'm going to do is replace this y with something. But we know that y has to satisfy this equation up here. So if I take that y and I solve for y here, I get 23 minus x. Now if I bring that down here and rewrite this equation for p, we get x times 23 minus x. And now if I distribute through, I get 23x minus x squared. Now all you have to do is give me x, which would be one of the numbers, right? We could have called, like over here, our first number is x, our second number is y. You give me just one of those numbers, and I should be able to tell you what the product is. Now, since I can do that, my p is now a function of one variable, so I say p is a function of x. And now what we're doing is, that was a notice that my headset, I don't know if you saw that, my headset battery is getting ready to die. It's not a good thing. So now what I need to do is try and find the maximum of this. Now, what I do know is that x has to be bigger than 0. because we won't even look at the negative numbers here, because we need to, well, I suppose we have two negative numbers, so we should look at that. So let's not even restrict our domain. So how do we find maximum minimums of a function? So the way we do it, first thing, take derivative. Through this is 23 minus 2x. And then we set that equal to 0. So the derivative equal to 0 means I set 23 minus 2x equal to 0. I solve for x. When I solve for x, I get that x is, come back up here, x is 23 divided by 2. So to prove that that's a maximum, that that's where I'm going to have a maximum, that p will have a max, what I do is I take my number line, I put my critical number here, 23 over 2, splits up my number line, and now I pick some test points. So I pick something to the left, pick something to the right of that. Now 23 divided by 2 is 11.5, so I can pick anything to the left of this, so how about I pick 1? Anything to the right of that, so how about I pick 20? And what I'm going to do is I'm going to plug those values into the derivative, so I'm going to plug them in right here. What I'm looking for is, positive and negative will tell me if I'm increasing or decreasing. So if I plug 1 in here, so take 1, plug 1 right in there, you get 23 minus 2. That's going to be 21. That's a positive number, which means my original function p is going up here. And then if I plug in 20, you get 23 minus 40. That's a negative number, so that tells me that my p is going down here. So that means this original product function goes up and then goes down at this 23 over 2, which means that 23 over 2 is a maximum. So if I let x be equal to 23 over 2, I should be able to get y now. So I go back over to the equation over here on the right for y, and I plug in what x is. So that means that y is equal to 23 minus 23 over 2. Those are my dogs that just won't be quiet. I should say my wife's dogs. 46 over 2 minus 23 over 2. So I get a common denominator there. So y is also equal to, if you subtract there, you get 23 over 2 again. So that tells me that my x and y are going to be the same number. So to answer the question, if my smallest number is 23 over 2, my largest is 23 over 2, and of course they're the same number. Now, if we take those two numbers and add them together, let's just check that this works. If we add those two numbers together, 23 over 2 plus 23 over 2, I should get 23. So of course you add this together, you get 46 over 2. And that is 23, so that checks. But now if I multiply them, 23 over 2 times 23 over 2, I get, let's see, 23 multiplying straight across, get 529 over 4. So that gives me 132.25. So as you can see, 132.25 is a little bit bigger than the 132 here. In fact, 132.5 is the maximum product that I could ever get with these conditions. So even though the table was pretty good at giving us an idea, the calculus gives us the exact answer. All right, moving along. Find the dimensions of a rectangle with a perimeter of 100 whose area is large as possible. So let me start with a picture. I have a rectangle. Rectangle has, I'll say, x and y. And what I know is that the perimeter is 100 meters. Now the perimeter is the total distance around. So total distance around this thing is an x plus a y plus another x plus another y. So my perimeter is going to be 2x plus 2y must be 100. And just to make this equation easier to work with, I'm just going to divide everything by 2. So now this is my new constraint equation. Now let me go try and figure out what it is that I'm trying to find the maximum of. I'm trying to find the largest area possible. So let me write the equation for area. The area of this rectangle is x times y. Now again, my area depends on two variables, x and y, so I'm going to try and rewrite it so it has only one variable. So I'm going to try and replace my y here. So I'm going to go to this equation over here, my constraint. I'm going to solve it for y. If I solve that for y, y is equal to 50 minus x. And now I'm going to plug that in over here for y. So I get 50 minus x here. 50 minus x. And now this means that my area is 50x minus x squared. And I can now say that my area is completely a function of x. And that equals 50x minus x squared. Now, I should talk a little bit about domain here. It is possible that it is not possible for us to have a rectangle if x is a negative number. So I'm going to say that x must be greater than or equal to 0. So I'm only going to be looking on the positive side or the right side of the number line for answers here. So the way we figure out where this function, this area function, will have a maximum is to, again, take its derivative, figure out where it's 0. We also want to look at where it's undefined, but we're not going to have to worry about that because it's a polynomial. So let's take our derivative. The derivative, actually, we want the derivative set it equal to 0, so I'm going to do it all at one step here. Derivative of a is 50 minus 2x. I want to set that equal to 0. Solve for x. I get x is 50 over 2. Then I draw a number line, 50 over 2. All right, oh, 25. I should just write 25, huh? Let me just erase that, 25. That breaks up my number line. I'm going to pick test point here and here, plug those into the derivative. So how about 1? I like 1. And how about 30? Plug those into the derivative. So I'm plugging those into my derivatives right here. And forget that that 0 is there for right now, because all I'm doing is evaluating the derivative at those 2 points. If I plug in 1, get 50 minus 2, it's a positive number, so I know that my area function goes up here. And then plug in 30, we get a negative number, so area goes down. That means that I get a maximum when I let x be equal to 25. So if I let x be 25, then I can solve for y using that equation. That means y is 25. So what that tells me is that if you're going to draw a rectangle that has that you want to have a perimeter of 100 meters on, then to get the maximum area, you actually need to make your rectangle be a square. So 25, 25, we're done. I really don't know how much time I'm going to have with my headset, so it might just die, and if it does, I'll have to stop the video. Okay, find the dimensions of a rectangle with area of 343 meters squared whose perimeter is as small as possible. This problem is like opposite of what we just did. I'm given in this problem the constraint that the rectangle has an area of 343 square meters. So I have a rectangle, x, y. I'm told that the area is 343. Well, the area is x times y, so I know that x times y is 343. So that's my constraint. Now, what is it that I'm trying to find the maximum or minimum of? In this problem, it's minimum. I want to find the perimeter is, when the perimeter is as small as possible. So I need to write down what the perimeter equation is. The perimeter of this, we already know, was 2x plus 2y. And I need to get this all in terms of one variable. So I'm going to replace my y in the problem with whatever this equation gives me. So I need to solve this equation for y. Let me do that. Y is equal to 343 divided by x. So I divide both sides by x. And I take that and I plug it in over here for y. So my perimeter is 2x plus 2 times 343 over x. And now what I'm going to do is I'm going to clean that up over here. And my perimeter is now a function of one variable. So I get 2x plus, I can just multiply that 2 straight across. So 2 times 343 gives me 686 over x. Now I'm going to need to take derivative of that. I should also mention that x here has to be strictly bigger than 0. It can't be 0 because if x is 0, then I would have undefined right here. So x has to be a positive number. So because I know I need to take derivative, let me just rewrite it first so it'll be easier to take derivative. What I'm going to do is I'm going to bring this x that's on the bottom up. So 686 x to the negative 1, and that way I can just do the power rule. So my derivative is equal to 2 minus, so I'm bringing that power up front, remember, 686 x to the negative 2. Subtract 1 from the power. And what I need to do now is I need to set that equal to 0. So let me rewrite it again so that you can work with it a little better. That's our derivative. I want to know when it's equal to 0. Little dog has a barking problem. Set that equal to 0. So the way I'm going to solve that is I am going to move this entire term to the other side, which makes it positive. 2 equals 686 over x squared. I'm going to multiply both sides by x squared. These cancel on the right side. Left side I have x squared times 2. I'll divide the 2 on both sides. That'll give me 343. And then I take the square root. So I take the square root of 343. And that's not a nice number. You get, well, I'm just going to say square root of 343. We might have to simplify that later, but that's what it is. And as a decimal, it's about 18.52. So it's approximately 18.52. Now what I need to do is make sure that this is where we had a smallest possible value. So the only way to check that that's true is to take a look at the number line, break it up, and test some points. So be careful, because when you do this on a test for the final, if you just get this answer and you never check to show that it's a max or a min, depending on the problem, you'll get points taken off. So I have to verify that this is actually a minimum point. So I break up my number line. I pick any number over here, but remember I have to be bigger than 0. So how about 1? And over here, let's go for 20. And what I'm going to do is I'm going to plug those into the derivative. Remember, the derivative was 2 minus 686 over x squared. That was my derivative. So when I plug in 1, what happens here? Plug in 1, 686 divided by 1 is just 686. 2 minus 686, that's a negative number. That means my perimeter function is going down here. When I plug in 20, if you do 686 divided by 20 squared, right? And I'm going to get that as a decimal. It's going to be 1.75. So 2 minus 1.75 is a positive number. So that means my perimeter function is going up, which means I do have a minimum value at 18.52, or square root of 343. Now that's just what x is. I also need to find what y is. So go back. Remember,